2.2, we'll explore limits that include infinity in them. So we talked about this function, f of x equals 1 over x, on Thursday. We said that as x gets super big, the denominator of this fraction becomes big, which means the actual function value is closer and closer to 0. We said the same, so we say the limit as x approaches infinity of 1 over x is 0. And also, if we let x approach negative infinity, we have the same kind of thing happen. So we could say that the limit as x approaches negative infinity of 1 over x equals 0. Just notice, here's what's new for today. We want to understand the connection between that and the idea that if I drew in the horizontal line y equals 0, I'd have a horizontal asymptote for this graph. So remembering that we can investigate limits by making a graph with our graphing calculator, or using a table, or using algebra, stop the video and fill in the picture, and with maybe a table, for the other function that's there, the second example. So I expect you would have seen for that second example a similar picture, but shifted, and so that there's actually a horizontal asymptote in a different place. So we would actually want to correct this here. This should say there's a horizontal asymptote at y equals b. This is the definition of a horizontal asymptote. If you can find a limit as x approaches infinity of a function, then whatever that value is, that's the location, this is a b, of a horizontal asymptote. So here in our function f of x is 1 over x, we said the limit as x approached infinity of 1 over x was 0. That means that this function has a horizontal asymptote at y equals 0. And it turned out that as we let x approach negative infinity, we got that same limit, so that we have another way of finding that same horizontal asymptote. Now some functions actually have two different horizontal asymptotes, one that they approach as x goes toward positive infinity, and one they approach as x goes toward negative infinity. So let's check out this example. You might want to graph it on your calculator too, this function, to see what it looks like for a function to have two different horizontal asymptotes. So one way that we can explore limits, especially as x goes toward positive or negative infinity, is to talk about what parts of them become significant or insignificant. So think about this. I'm going to find the limit as x goes to infinity of x over the square root of x squared plus 1. Think of x as a really big number. I'm going to let it get bigger and bigger. This little plus 1 down here is going to have less and less effect until it has practically no effect at all. So we can use that algebraically to think of this limit as the same as the limit as x approaches infinity of x over the square root of x squared. But that's something we can simplify algebraically. The square root of x squared, as long as x is positive, is just x. Now we want to take a limit of x over x. Well, x over x, no matter what you do, is always equal to 1. So the limit as x approaches infinity of x over the square root of x squared plus 1 equals 1. And based on what we learned in the last couple of slides, this means this function will have a horizontal asymptote at y equals 1. Similarly, we can consider the same function as x goes toward negative infinity. Still, my little plus 1 is going to have less and less effect until he has no effect at all. So I can think of this as the limit as x approaches negative infinity of x over the square root of x squared. The thing about the square root of x squared, when x is negative, the square root and squaring don't just exactly undo each other, because this radical sign means to take the positive square root. So I'm actually going to end up with the opposite of x down in my denominator. So my new expression is x over the opposite of x. When you divide a number by its opposite, the result is always negative 1. Well, if the limit as x approaches negative infinity of this function is negative 1, then by definition, there's a at y equals negative 1. And again, if you'll graph this function, y equals x over the square root of x squared plus 1, you'll see that it approaches two different y values as you look furthest to the right and furthest to the left. So we'll wrap up with this big idea that we're going to investigate limits as x approaches positive or negative infinity by considering which terms, which parts of the expression dominate as x gets bigger toward infinity, or very small toward negative infinity.